Recording. All right, guys. Every time I tell people to log back in, I don't know what happens. But now we were around 84, I see 66. Hopefully they'll come and join us very soon. But before I continue, can you guys hear me? Are you hearing me, please? I know some people have issues. I want to make sure that things are okay on my side before we go on. Okay. That's fine. That's fine. Okay, let's continue. Please encourage your friends who have gone off to log back into the session. Right. Properties of even and odd. Clearly here there is nothing big. You know, a negative is associated with a function being odd. You know, a positive is associated with a function being even. Even in linear algebra 1, you did this kind of verification. So you remember when the first time they subjected you to computing the determinant of a given matrix. Remember, you had the permutation method, the permutation and the inversion technique. And you remember, even a 0 was considered as a negative, a positive. So it's the same thing here. Here, of course, when you talk of odd even, again, you're talking of the positive and the negative, and the same applies when it comes to the multiplication kind of operation. So you know that if I have a positive and I multiply it with a negative, I get a negative. What does this mean? A product of an even function with an odd function gives me odd. So positive here, in this case, it is even. This is even. And the negative in that case there is odd. So even odd is odd, then you know, of course, commutativity works. You know a negative and a negative is a positive, implying a product of odd and odd function gives you an even function. And lastly, I think it is the even and the even, which gives you even. I don't think I've left out anything. The others, it is just commuting, if you use the commutativity property. So this is basically what we are saying. So this is what we are saying. The product of two even functions is even. That is this scenario here. Is that okay? Then you substitute and the proofs are direct. Me, I'm not going to bore you people by going through these proofs. This is obvious. You know, by definition of even, this is true. So if you have two functions, f and g, you have that function, you have this function. I've already demonstrated this. If you look at the product of this is like a composure of the two functions. You did composite functions in the calculus 1. So we are picking it up from here. So if I unify this using phi, the big phi, which is this one here, okay, it means this dot that is this term here, and then I substitute. Remember, it's minus x here. So expanding that out to give me this, but remember, we have been told if you take this and this out, remember they are even functions. Maybe what is missing here, just let me include something that is missing in this step. The only thing that is missing here is we know that, okay, it's not this. We know that if it is an even function, rather, yes, if it is even, f of negative is positive, which is that one. And we can do the same for odd. So the fx.gx is the big phi x, which is now this being equal to this term here. Is that okay? And if it was negative, remember we said the odd and the odd is even. So if it was odd and the odd, this will give you minus fx. And then you do have minus gx, but you know minus minus is positive. That is the product of both two odd functions gives you an even function. Right. So from that we can proceed. Okay, you go through all of these proofs. There is nothing really threatening here. Everything is as obvious as you have discussed it before in calculus 1. I told you you'll have prerequisites here of Cal 1 and Cal 2. Okay, differential calculus and integral calculus. So just to borrow from those two, that one should be fine there. There are examples here. This is now from integral calculus. I also don't have to waste time in this 6th property. This is property 6. We are going to apply this because what we are going to discuss right now is understanding a half range, or when is a function even, when is it odd. Okay. So what do we have here? We have this property. The first one, which you can go ahead and verify. If you move from minus a to a, this is the same as having twice the integral of 0 to a of fx. This property, you fully discussed this and even verified it in calculus 2. That was integral calculus. Of course, here I am talking to those who took time to understand what was being presented to them by that time. But those who are obsessed with simply passing, you may have passed in the 3rd year, but none of this now makes sense. Okay, so go through all of these proofs are examinable, guys. Please make yourselves happy. Go through this proof. This is your Cal 1. I'm not going to waste time on this. And besides, in the first topic, we applied a number of these concepts. You remember when we are changing limits, and we discussed this a lot. I will be ridiculous to go through something I have already been discussing. Convolution, when we discussed the different methods of solving piecewise systems, especially when we're talking of a Heaviside function, we applied these ones. So I'm not going to waste time on this. And if you go through, you come to the conclusion that this is it. Please, here you don't even have to get your hands dirty, but simply wash your hands. By washing your hands, I am saying you already know this. Simply clean off the small dirt. By the small dirt, I am saying what you have forgotten, so that you can easily remember how we arrived at this. Okay, the last property, which is this one. We are saying, here we said in this one that if you integrate from minus a to a of fx dx, it is to the integral from 0 to a. This one is going to be used heavily in what we are going to discuss now. We are going to heavily use this one here, guys. And we will also heavily use the 7th property, this one here, because when we integrate, this one will help us understand why the sum Fourier coefficients immediately go to 0 without even going into a computational kind of stress. So here we have a small statement. It could be a theorem that if fx is odd, this function, if it is odd, then from minus a to a of fx is 0. But if it is even, it is twice 0 to a f of x. Okay. So again, we go back. We know the definition of an odd function. So to complete this kind of range for the integral, you can move from this is minus a to a. So given that this holds, you have this statement here, that is f of minus x dx. Remember, we are talking of an odd function. And because that is the case, remember by definition of an odd function, if you're dealing with this as an odd function, we have already said that from the examples we've discussed before, that odd and odd is even, and then even odd is odd. So if you look at this here, you would literally have moved from minus a to 0. I think we are clear there. If you move from minus a to 0, then we can use the other property where you, I think we already have that property up here, if I'm not mistaken. Where is it? We have that property, I think. Somewhere here we used it. In this step, you have, this is from, there is a mistake here. This is supposed to be from minus a to 0. But if it is from minus a to 0, you can take the negative out and it simply becomes from a to 0. And that is what we are using here. So this should have been from minus a to a of that function. But remember, there is a negative here. So since it is this, remember we are dealing with an odd function, it is a negative. But now, when you change, because it is from minus a to a, you now change the order of the limits, which is 0 to a, which is minus, because this negative here, you can just throw it out. And throwing it out is equivalent to, the property I'm saying is, if you have, this is a, b, this is minus the integral, this is b to a. Please, you need to go and you revisit your calculus 2. That is the property we are playing with here. And because of that, remember they are already odd. This is a positive, because here you are moving in the positive domain, that is from 0 to a. Here you are trying to exhaust this function here. This function exists in the negative and it exists in the positive. That's from 0 to a, you have a certain fx, and from negative a to 0, there is a fx dx. Then from 0 to a. Is that okay? But since from 0 to a, it is in the negative domain, this is the f of minus x. That is this term here. To cater for that. But remember, again, negative a to 0 is the same as minus, it's the same as, if you have negative a to 0, that is the same as minus 0 to a. And because it is minus 0 to a, all right, if you take this, if you compute this, this one will definitely give you a negative over that. And that giving you a negative over that, you will now get the term that you have here. And once you have this positive here, you end up with a 0 there. Okay. Now, when we talk of Fourier, now what we have discussed in these properties is going to be very key in what I'm going to present next, guys. Can I hear a yes if you're still there? I don't, I may be here when I am talking to ghosts. in a virtual mode. You know, even when you access some computer programs, they will say, please tick this box for us to confirm that you are not a robot, or choose what looks as a road to you. And once you choose, then they will verify, because in robotic kind of engineering, it is not easy to impart everything into that knowledge, into the robot, so that it can know this is a plane, this is a road, this is. So for me, I'm using a yes. And I have got 15 yeses, a clear indication that I am with you. Okay, I can now tolerate the silence, because initially I thought people had gone for lunch. Okay, so I'm saying we're going to use a combination of these properties, these ones here, and then we understand a half range, and this half range, it will be understood in terms of a Fourier cosine and a Fourier sine. Okay, so Fourier sine, Fourier cosine, they can be directly related to half range and full range. Now, the beauty about what we are going to discuss now, once we understand what a Fourier cosine is, and we understand what a Fourier sine is, believe me, take it or leave it, all the other computation is simply the same as the computation we looked at in the first example of this analysis. All of those computations are directly the same as these ones here, if you recall how I did these numbers. Okay? Okay, that one at least is promising. That should tell you that what we are dealing with is something lighter, not abstract as a naked eye may suggest when you look at it. Okay. So here we are, after getting to know the properties, now let us just modify or kind of hike up our definition and understanding of these Fourier transform, Fourier coefficients. But this time, with the specific to a cosine and a sine, and if the function you are dealing with that has come through as your fx is positive, that is even or odd. So we are looking at this, the modification is going to be on these terms here. Is that okay? And the modification of these terms will depend on whether the function is positive, or rather whether the function is even or odd. And in this case, you're saying that the function is even or odd. You don't have to first verify that it is even or odd. What is key is, have you been notified that it is odd or even? Unless they tell you, first verify and then go ahead and compute. Okay, so the definition is the same of our Fourier series. And after understanding this Fourier series, we have looked at this Fourier coefficients, and what we call a Fourier series expansion here, we are indirectly saying that what we are dealing with here is full range. Is that okay? That is full range. By full range, you are moving from minus L all the way up to L. Oh, my error is big. Pardon, believe that this is a normal error, especially the Weizsäckers. Okay, so we can now go ahead. Moving forward, we can now look at the modification. So the question is, given if I would call the whole of this equation 1 and the whole of this 2, the modification is going to be in N0, An, and Bn. So what if fx is odd? What happens when I talk of fx being odd, guys? I want to be clear. The fx we are talking of is simply that term. Meaning this term is going to perturb this function and causes changes. By perturbation, I'm picking from what Dr. Nakakawa discussed with you in dynamical systems. I am sure in there you looked at the perturbation theory as a form of establishing the stability of a system. So here when I talk of perturbation theory, you have already interacted with the term or the theorem in the dynamical systems. That shouldn't be a problem. So this function here, if it is odd, then we'll see that the Fourier coefficients, these expressions will change. Why? That is what we are going to look at. Implying what? So if we have the integral a naught, we've started modifying this. If we have the integral a naught, remember we are saying fx is odd. And remember in property 6, for those who may have already forgotten what I have just discussed, property 6, we said that the integral full range from minus L to L of fx odd, that would give you a 0. This is calculus 2. We've talked of that right here. That if you integrate from minus a to a of fx dx, that would give you 0. If the function is odd, I think I'm clear there. Okay, guys. So we'll catch up. Okay. Yes. Yes, my dear students. Let's continue. If we have fx, we are saying fx is odd. Okay. So I am referring to property 7, sorry, not property 6, property 7. We said if fx is odd, then that integral is 0. So this is a direct application of the, properties we've seen, rather we've discussed. Okay, so we are here. This is what we are applying now. So if fx is odd, you have the integral from minus L to L of fx. I hope we are together there. So since it is odd, so integral of an odd function, it will give you 0. So when you get a 0, this n naught is a 0. Okay. Then what about an? An on a full range, guys, we got 1 over L minus L to L fx cos x. I hope we are together there. Now we are told that the fx is odd, but we all know that cos of x, that function is always even. This one now, that it comes in handy for you to know. You all know that cos of a given angle, cos in the generic form of minus x. I think you are all aware that this is simply cos x. Because we are saying cos of minus x is cos x, it implies that f of minus x, this is fx. I hope we are together, guys. Cos of minus x is cos x, and this deduces to our definition of what an odd rather even function is. So cos alone, here we know it is even, and if you apply that concept in here, fx is already given if fx is odd, right there. Then what is cos n pi lx? I have used the generic statement here that cos of a negative will always be a positive, which is this one here. So the fx which is odd is this term here. Oh, it is this term here. Then we bring in the even part for the cos. We have already said that the product of odd even is odd. Over we are together. So this product here, that is odd, a negative times a positive gives us a negative. This is odd function multiplied by even function. The product is odd, and the product being odd takes us back to this guy here, and we said it is 0. Therefore, that one is 0. Surely even the Kurama should understand this one. Okay, we do the last one. So far we have a naught. The first Fourier coefficient a naught is 0. The second Fourier coefficient, which is an, is also 0. We deal with the last. The last one is easy. We know that fx is odd for letter O, and you're, of course, you know minus, sine of any given angle. If I call it x or theta, this will be minus sine x. I hope this one is evidently clear to everyone. This one goes back. So if I try to relate this with our definition, it implies that that will mean that you have a certain f of minus x, which simply gives you a minus f of x. I hope we are together. So fx is odd, but even the sign here is odd. Remember, we say the odd and the odd is even. All right. And now here we use property 6. What does property 6 say? What does property 6 say? Property number 6 is right here. Property number 6 is here. Did we state it? Okay. You see our property 6? Property 6 is right here. We have said that if you have, I think you can see that, integrating, remember we said if fx is even. If fx is even, the integral from minus a to a for range will simply be twice the integral from 0 to a. That's what we are trying to do here. So this property holds, and since that property holds, we now go back. If we go back to what we have been trying to do, where? Here. Yes. It means that this is odd, and it being odd, the fx, we already know it is odd. What is sine? Sine is also odd. So you have odd, which is even. So since odd times odd is even, then it means the whole of this thing here is even. And it being even, remember we said it is 2 over what? It is 2 over L, which is, we only looked at, if you are integrating from 0 to what? We said if you're integrating from 0 to if you're integrating from minus a to a of fx, then if the fx here is even, then you'll have twice the integral from 0 to a. But remember, we already have a 1 over L. So there is this 1 over L, which is the 1 over L there. Then since this is even, this product here is even. This is even. Okay, it being even implies that we'll get 2 over L integral from 0 to L over that function. All right. Okay, I was looking at the chart to see if there is something interesting. All right, so that is it. So now we can deduce that if you're dealing with a Fourier sine, I hope I am with you guys, that once you're dealing with a Fourier sine, and they have told you compute the Fourier sine, by default, by what we have done here, if you're told to compute a Fourier sine, it would imply that the Fourier coefficients A0 is 0, AN is 0. You'll only get BN, which is given by that term. And once you have fx, substitute it here, you know the L, substitute it here, integrate by parts, get the given, get the expression. I hope I am clear there. Okay, and with that understood, this is what we are saying, that in that case, so what we are doing here, for those who may not have understood how we have got this simplified version, this one here. This one, we are getting it from the general statement. Remember, A is 0. So A being 0, what would that imply? A being 0, it would imply that the whole of this is out. Then AN is 0, the whole of this term is out. So you simply remain with BN sine N pi x over L. And that's what we have expressed there, that this is approximated to be simply the sum from n equal to 1 to infinity of Bn sine N pi x over L. Okay, right. We need this, there you go, okay. So this is what we have in this red here. And we are saying with the coefficient Bn reduced to the Bn we have already seen, that our Bn here, what we have in the box is basically this one here. That is what we have as equation 3.6.2. And we are saying that this thing here is called a Fourier sine series. Anyone saying no? Because I may say this, but for some reason, or for some curiosity, you did things, and what I am saying is contrary to what you know. Given that there is a total silence, to me, that is an indicator that you're not just understanding, but you have overly understood what I am trying to explain here. So let us continue. Now, what if fx is even? I don't have to go back now. I'm sure property 6 and 7, they're on your fingertips. So this one will even be faster for fx being even. So fx being even, it would imply that this term here, fx is even, so this one is even here. If fx is even, we looked at property, that is property what? Property, I think property 7, where we said if it is even, you will get it as a 2 integral from 0 to L of fx. This is even. So you get this one. So for you to compute fx, rather n0, if fx is even, it is simply this computation. Then what about, remember we said that a positive times a positive, this is a positive. So even a product of an even function with an uneven function, you will get it as even. There are even proofs in the theorems up there. We have proved this, even and even is even. So here fx is even, that fx is even. We've already established the fact that cos x is even. So a product of even and even, it gives you even. And the property says if it is even, then the integral, which was from minus L to L, becomes twice integral 0 to L of that even function. That one is finished. So an will be given by that. And lastly, guys, Bn. What is Bn? Bn is 1 over L integral of that. And remember, fx is odd. Sorry, it is even, but sign is odd. Even and odd is odd. And we said if you have this integral, but the function is odd, it is 0. And based on that fact, we deduce that given that fx is a naught over that, and because the bn is 0, so you get the a naught and the an. That is why when you substitute back into this equation here, this one, okay? If you substitute back into that, remember it's bn which is 0. These ones are non-zero. You remain with this term here, the a naught and the sum of the an. So that gives us, where are we? We are here. That gives us this term here. That is the fx, the approximation of fx will now be a naught over 2, and then you have sum of an cos of that one. Okay, and what is this called? This one is what we call the Fourier. We'll call this one the Fourier cosine. I hope we are together, guys, there. So what remains is, guys, I'm remaining with some 7 minutes. So just log back in for just those 7 minutes. I promised I am finishing at exactly 2. If you could log back in very fast, then I highlight these examples that we have here in those remaining 5 minutes. Please log back for just 5 minutes and we finish up the examples associated with these derivations. I hope I am clear there. Just come back again and we finish at exactly 2. We are going to highlight those examples. Okay. Oh, I need to clear this first. So there are some examples here now, and these examples, all we need to know is the function